Hi, welcome to the International Space Station Flight Control Room. As promised, we have a guest with us here on the PAO console today, Paul Abell, who is the lead scientist for Planetary Small Bodies, and he is going to tell us a little bit about subjects I think is of interest to a lot of people, the meteor that hit the ground in Russia on Friday. Thanks so much for coming, Paul.
Thank you very much for having me.
Well, okay, so tell us what exactly happened on Friday. Let's start there.
Okay, so Friday morning, about 9:20 in the morning, Russia time, we had an object that came in and it exploded in the upper atmosphere over Chelyabinsk, Russia. It's a town in the southern Urals in Russia.
Okay, and it was a meteor?
Yeah, it actually was a small asteroid or a big meteor, either one. The asteroid was about 15 meters in diameter. Came in very fast, about 18 kilometers per second, and we think exploded at an altitude of about 20 kilometers.
So it exploded before it hit the ground. It didn't actually hit the ground, I guess.
Yeah, that's right. So this was an airburst. Meteorites hit the ground. This actually object didn't hit the ground intact. It actually burst or exploded about 20 kilometers up, and fragments actually fell to the ground. So right now, what the Russians are doing are actually trying to recover those fragments.
Do you know anything at this point about what the meteor was made of or where it was coming from, anything like that?
Yeah, actually, we think the meteor or the asteroid was made of rock. So we think a 15 meter diameter rocky asteroid. The reason we think that is because it had actually burst at altitude. If it was a solid iron, it may have made it all the way to the ground before exploding in the air. We also have some fragments. Initial reports from the Russians suggest it may be a rocky material.
What causes it to explode in the air rather than go all the way to the ground?
So rocky asteroids are a little bit weaker than the solid iron. If you think of battleship armor, it's very, very tough, very, very strong. Rock is not nearly as strong, and moving so fast, it gets to a certain point in the atmosphere where the density of the atmosphere, the lower atmosphere, causes the asteroid actually to explode. It can't punch its way through, and that's why they had the airburst.
Okay. And I guess it's unusual, or fairly unusual for one to make its way through our atmosphere at all, right?
Yeah, usually the ones that have to make it through the atmosphere are intact at hypervelocity are much, much bigger. You think about the dinosaur impact 65 million years ago, that was a much, much bigger asteroid. That was about a 10-kilometer diameter asteroid. And that made an impact crater all the way to the ground in Mexico. This one was much smaller, like I said, 15 meters in diameter, and it exploded at altitude. Some piece of it actually made it to the ground, but they just fall. They don't come in at high speed.
Okay. And how often would you say that that happens?
So we get hit by material all the time. The Earth sweeps up about 80 to 100 tons of meteorites, meteor material. So there's a lot of stuff falling on us, but it's usually very small, and we don't notice it. Our atmosphere protects us, so that smaller size stuff we don't really worry about. Something like this size and a little bit bigger happens maybe once every 100 years. The last time we had an event of this magnitude was in 1908 over Tunguska, Siberia in Russia as well, but that was a much bigger object. It was about a 50-meter object, and that exploded again at altitude, but had much more energy associated with it.
Okay, so they're reasonably rare. We don't have to worry about one happening every day. The two that you mentioned both were over Russia. Could it happen anywhere?
Yeah, these objects come in all the time. We have basketball-sized things hitting the Earth, probably about once a month. The reason why these things happen in Russia is Russia is just a big landmass. It's just a coincidence that the last big one happened in Siberia. This one happened in the southern Urals. Russia is just a very large landmass. There's nothing unique about Russia. These things don't have an agenda against Russia. It's just Russia is a very large landmass, and these things happen and fall all over the world. In fact, we have meteorites in Antarctica. We have a team that goes down there every year and recover meteorites from Antarctica. So this type of material, they fall all over the Earth.
And I know y'all keep track of a lot of what's orbiting in space, in part to make sure that the space station is not going to come across any of its paths, right?
Yeah, that's correct. So there's another department. So I am associated with the Near Earth Object Program, so natural asteroids and meteorites and things. And there's another program office that's concerning itself with orbital debris. And we track the orbital debris, and we make sure the station and any other satellites are safe. And if need be, we can maneuver out of the way.
Okay, and orbital debris is man-made generally?
Yeah, it's man-made space junk. It's bits of satellites, rocket bodies, things like that are no longer in use and still flying around the orbit of Earth.
And so a lot of times when we hear the space station has to move to avoid, it's usually something, it's usually orbital debris, right?
It's usually man-made. That's correct. It's usually orbital debris. Yeah.
Okay. Now, do we keep track of things like meteorites and stay out of their way as well?
So yes, just like we keep track of orbital debris, we keep track of these asteroids. We do have a survey program, ground-based survey program, that keeps track of as much of these asteroids as we can. Right now we have about 9,600 near-Earth objects being tracked and cataloged.
9,600.
9,600, yeah. And actually there's a lot more out there. This is what we know right now in our current catalog. The biggest is about 30 kilometers. The smallest is a few meters across. Just so you know the big ones, like the 30-kilometer ones, there's no danger from those guys, right? So the thing that we're working on right now is concentrating on finding all the 1 kilometer diameter sized objects and up.
1 kilometer, that's still pretty big.
Yeah, it's really big. And the reason why we concentrate on those is we want to make sure that the Earth is safe. The 1 kilometer and up, the bigger guys, are the ones that can give us a bad day, a really bad day, sort of like global devastation. So we concentrate on those first, and we're actually doing a really good job on those guys. We've got about 95% of those guys cataloged. We know where they are. They're not in dangerous orbits, and there's no threat to the Earth. We still got a little bit of work to do. We got about another 5% to find. And then we have to start working on the smaller ones, and this is where we need a little bit more effort and work, and we're working on that very hard right now.
How do you find them to begin with? Big ones or small?
Really good question. So one of the best ways to do it is through telescopes, right? These asteroids reflect sunlight off their surface. They don't give light off. They look like stars, except they move very quickly. So we use ground-based telescopes looking in optical wavelengths, just visible light, and we try and scan the sky, and we pick them up and catalog them and track their orbits that way.
Can you do that with just any telescope, or does it have to be a pretty powerful one?
It has to be a little bit sophisticated. We have some big telescopes. We have meter sky size class telescopes. We also have one space-based asset that has been helping us too, called NEOWISE, that currently is offline right now, but we're hoping to bring it back. It's been doing some great stuff for us. But the telescopes that are typically used aren't really big. They're not like the 8 meter or 10 meter class, but they're a few meters across. It's mainly more the software and the people behind them that do the job. And we also have, I should point out, some very good professional level amateurs. They don't get paid like I do working for NASA, but they're very good, and they actually help us out a lot, tracking and keeping track of where these guys are.
Well, that's interesting. A pretty big network, you said?
I wouldn't say it's a real big network, but it's a sizable network. It's an international cooperative network. We have telescopes in the northern hemisphere and the southern hemisphere, all over the world, and helping us keep track of these objects.
Well, that's great. So I know there was some confusion, though, on Friday about one of these larger objects that y'all had been tracking. I think DA-14?
Yes, 2012 DA-14. This was an object that was about 50 meters across, and we discovered it a year ago. And actually, it was one of these professional amateur groups that I mentioned earlier that actually discovered this particular object.
Wow.
And yeah, they did a great job, and we were able to track it. And we knew that it was going to make a very close approach to the planet, so we were all set up watching for that. The Russian event that happened was a complete coincidence. It was in no way related to DA-14, 2012 DA-14. The orbits are completely different. The orbit of the Russian event was an east-to-west entry, and the orbit of DA-14 was south to north. So no way related.
Okay, it's completely separate, just happened to take place on the same day.
Exactly.
It's a
Just
pretty big coincidence.
a remarkable coincidence, yes.
Okay. But now, so the one in Russia, if that had been over the ocean or something like that, would we have known about it?
Yeah, we would have known about it. I don't think we would have as good video, and when we had remarkable videos, and we're really anxious to look at that data. Basically, in Russia, they had all these dash cams and a lot of security camera footage. So it happened over a major city, population center, so we got lots of good footage. If it happened over the ocean, you wouldn't have the video, but we would be able to know about it. We have satellites in orbit that look for these type of explosions. We also have infrasound stations. These are stations set up to monitor big explosions, basically nuclear explosions, sort of part of the Nuclear Test Ban Treaty, and they monitor and listen for explosions. And so they would have picked up this event even if it had been over the open ocean.
So it's not happening every day, and we just don't know about it because it's not over city.
Exactly, yeah.
Okay.
We would know that. It's not happening every day.
All right. Well, what's next? What do you do at this point to learn more, or go on from here?
So one of the things we've got to do is, obviously, we'd like to recover as many fragments and pieces as we can. There's supposedly a very large fragment that fell in a lake, punched its way through the ice. So we're in the process of working with our Russian colleagues to try and recover that. We'd also like to get an idea of the composition of the object, find out exactly what was made of, and then do some more analysis and sort of fine-tune the mass and the size of the object. And like I said, it's between 15 and maybe 17 meters in diameter. Estimated mass is anywhere from 6,400 to 7,700 metric tons. So it was a sizable object.
Sounds like. What can you learn from the fragments?
Well, from the fragments, we can learn what the original asteroid. This is a piece of a bigger asteroid, so learn about where it came from. Back out its orbit. From the trajectory, we have a preliminary orbit, so we know that this was a near-Earth asteroid. Obviously, it came and crossed our orbit and hit the Earth. We want to know where it came from, how long it's been in space. We can get an idea by some of the fragments. We can find out how long it's been in space and when it was liberated from its parent body. That's very interesting from an orbital dynamic standpoint because it tells us how fast things come from the main asteroid belt, which is located between Mars and Jupiter, and how fast things get to Earth. So it's another test of that. We'd also like to learn about the composition because that tells us a little bit about its internal structure, its strength. So in future events, we have an idea of how far these things can penetrate into our atmosphere and how big a size range we have to be worried about before we have to take mitigation steps to prevent damage.
Wow, so lots to learn from that. And we do that kind of work here at Johnson Space Center, right?
Yeah, we do. We have Astromaterials Research and Exploration Science Directorate, which I am a part of, and we analyze samples, and we can get all that type of information from the samples that we bring back here in our laboratories.
Or do you think you will get some samples from this to analyze?
The goal is to get a sample, at least some samples from this event, bring it back to Johnson, and find out all we can about the object.
Okay, well, maybe we'll have to check back in with you then after you've learned a little bit more.
Certainly.
Thanks so much for talking with us. Again, this was Paul Abell, the lead lead scientist for planetary small bodies.